Thank you everyone for joining us for the second day of the BTR 8 Western Track. We had a very engaging first day yesterday with seven Western Track sessions, and today we look forward to another exciting day. I'm Suman Mitra. I'm an associate professor of civil engineering at the University of Arkansas, and I am a co-chair of BTR 8. Before we begin today, I would like to take a moment to thank Dr. Kara Kokelman for starting this wonderful conference in 2022 and for her continued leadership in bringing our transportation research community together. Following the keynote, we have 8 Western Track sessions today. Uh, and these sessions actually have 4 parallel sessions from 11 a.m. to 1 p.m. Central Time in the US, followed by another 4 parallel sessions from 1 to 3 p.m. The sessions cover a broad range of topics, including transportation planning, electric vehicles, transportation resilience, transportation equity, network analysis, and travel behavior and modeling. And I hope that you all will be able to join us for these sessions as well. And now it's my great pleasure to introduce today's keynote speaker, Dr. Marta Gonzalez. Dr. Gonzalez is a professor of civil and environmental engineering and city and regional planning at the University of California, Berkeley, and a physics research faculty member in the energy technology area at Lawrence Berkeley National Laboratory. Dr. Gonzalez's research focuses on urban sciences, particularly the intersection of people with the built and natural environments and their social networks. Originally from Venezuela, she has never lost sight of the vast global inequalities that exist across our cities and communities. She has devoted great energy throughout her research career to developing robust solutions for sustainable cities in both developed and developing countries, drawing on new technologies and cross-cultural understanding. And to that effect, Dr. Gonzalez and her collaborators have developed new tools that have significantly contributed to transportation research, as well as novel approaches for modeling human mobility and the adoption of energy technologies. Our ultimate goal is to design urban solutions and enable caring development in the use of new technologies. For her globally impactful work, Dr. Gonzalez has received numerous recognition, including awards from the United Nations Foundation and the Bill and Melinda Gates Foundation. He was named a Fellow of the Network Science Society in 2023 and received the prestigious Lagrange CRT Foundation Prize in 2024 for her contributions to complexity science. We are very excited to have her with us today. Our keynote presentation is titled Towards the Science of Cities, a Complex System Approach. And before we begin, a quick note to our audience that we will reserve the last 10 minutes of the keynote for the questions and discussion. So please feel free to post your questions in the chat box at any time during the presentation, and we'll try to address them during the Q&A session. Now, please join me welcoming Dr. Marta Gonzalez, and feel free to use your reaction to give a warm virtual welcome. Marta, the floor is yours now. I'll stop sharing and you can share your screen.
Thank you for inviting me to this very inclusive presentation. And I particularly come from a different background. My background is statistical physics of complex systems, and I would like to give you a review of how I entered the topic, and hopefully we have a nice discussion at the end. And the way I entered into this field is because, as you already know, we gave up our privacy to be in constant information with technology. Every second, there is petabytes of information in the cloud with longitude, latitude, and time of people all over the world. And that has changed business with as all the companies that I'm showing there, Waze, Tesla, Google Map, you name it. Then the opportunity is, of course, how from the research world we can leverage all this data, particularly for transportation technology. Then the type of questions I would like to address today is how can we develop data science to help sustainable transportation and to inform city planning and what I like to call city science. So not only how we develop new applications, but also can we learn new things. I remember I come from physics. So I see my research in a Venn diagram. My original background is from network science. And there we have been developing some influence of AI technologies like computer vision, natural language processing, and some optimization aspects. And we would like to address urban planning, public service, Internet of Things, transportation systems, and statistics. So how we combine these two fields to create what I like to call, and that we work together in what I call city science. So the first aspect I'm gonna talk about is how we can leverage these data sources to generate demand models of mobility. And as we know, the traditional methods, thanks to which many of our cities were built, have this typical framework in which we have input data, usually coming from surveys, population synthesizers to do activity generation, and then do our micro simulations. Many times we would optimize the choices of route, of activity, so people would be optimizing their preferences. And we had demographics, and we could do beautiful synthetic populations. The disadvantage of these simulators were very hard to calibrate because this bottleneck, the input data. We always rely on surveys that only would cover 1 to 2% of the population. What drove me more into this mobile phone data is that in Latin America, we would pay for the survey for a consultant company to give us the demand model, and it would slow down the applications, right? Because 1 year to get the proper demand model because of the surveys. Then the opportunity is we want to know uh, the models of where and when and how people choose to travel. Then we want to have a representative sample of the entire population, and that's very important because this data have a lot of bias, and we don't have complete information of when people is moving. Then the typical data that became available at the beginning, it was through not so transparent and non-disclosure agreements for a business collaboration, but now many of this data is available for purchase. Typical data that one can use today to do the demand models in the new way adapted to this data is smartphone data, also called location-based service data, the usual call details record, for short CDR. Nowadays, there are brokers of credit card transactions, and social media is the one that most of us can crawl, scrape, and is not so hard to get. Then the idea is, because the data is very incomplete, biased, we have relied not on the choice models, but in some discoveries of patterns that we call the emergence of patterns coming from the complex system approach that is similar to the title of my presentation. Here I'm giving you an example of the LBS, location-based service data, and we have in the visualization, it looks incredible because it's 10 months of only one active user. And you can see there, for example, here in yellow, home and work. Then the first aspect, we have longitude, latitude, and time. We need to do DB scan, or what is called a parsing trajectories, that we can impute home, likely to be home, likely to be work, all the other places people stay. And when the people is not stay, open area of research is how can we assign routes, and the one that has been less easy with this data, but this open question is mode imputation. What mode people is using? Because as you know, already a map matching in GPS is hard. Imagine with this sparse data. Then let's talk about the sparsity I'm talking about. I show you 10 months. It looked like a lot of information from somebody. Remember, we gave up our privacy. Then this is an example of the original data set, only a few hours. And here is the y-axis of in a given distance, and you see all of jumps, right? It's not clear at all. If you do machine learning algorithms to predict behavior, in a few words, garbage in, garbage out. You can be predicting the result as sparse as the input. That's why we need a little more, less robust algorithms than just the algorithms from computer science that are available. Then one aspect, and it's a key advantage, and this figure in the right come from a early transportation research C that we published. So here again, you have different colors is different locations. This is a very sparse user. For example, it only have 5 calls in the day, and we have 5 different locations. However, when here is the key component, even if the data is sparse, when we see the person for many months, that is the typical with these devices, because it's not a survey, it's sparse, but the advantage is that we have a lot of time. We see that we can build a network, and in the network we then can create the transitions, and then we have the preferred visited location and a few locations that are visited only once. Then you have what we call the preferential returns, our repeated locations, and the exploration. And that was a key component to develop these models and to fill these metrics. In the map in the left, I'm showing on purpose how not good the data look like because it's sparse. People appear and disappear, and we're trying to build these networks with complete trajectory. That is the first intellectual challenge I would like to give you. And we come from one user at a time. Each time I need to see if the person is going to move, yes or not, and where, when and where. And I'm using the typical exaggeration. If we don't know anything about one particle or person that is moving, it's going to be a random walk. Of course, people do not have these trajectories as a random walk, but we need to do this same question is, at every step, person move, yes or no, and where they move. These come from data. So these are in this paper already one decade ago, we created this framework to complete the trajectories. Then there are 4 aspects, 4 ingredients to create these non-random walks of humans. That is the circadian rhythm. You are going to move depending on the time of the day. This is a probability of movement. The mobility rates are, if you are going to visit an exploration, you are going to stay where you are, and you are going to leave your house or not. This, I put it in a 3D plot because these mobility rates are unique to each person, and we capture from the data, and this express the heterogeneity in the population. And then we observed that the more places you see somebody, the less likely they are to visit a new location. So you have a limited number of locations, and also there is a key component that is in the complex system community doing mobility design. We call it the preferential return. You are going to select a location you have already visited depending on the time you already visit. So you prefer to return to the places you have already visited. And then this is the hardest, and this is the family of the intervening opportunity. You already know if you're going to go back to a location that you already visit, you prefer to go there. But if the person never has been there, where you're going to go, and this is the rank of the destination based on the visit of everybody. So if people, you rank the locations according to the trip attractions they have in the map. And when your agent is going to explore a location, you use this ranking of your exploration. Think again about the intervening opportunity model. This is completely different from the typical choice models, but at the end of the day, here is how we summarize it. 4 ingredients. At every step you do something. A decision is a Markov model because at every step you need to decide where the person is going to do and what you're going to do. You can stay or you move or you explore or you return. That is the key components. Here is how it's expressed. Some of the discoveries is that is very interesting. These rates that I show you that give you the heterogeneity among the people. Uh, Jungpin, you have a question or no? No, I guess it was by mistake. So once the person enter into a flexible activity, you get 10 times more possibility to move. And those are the excitation rate. And that is how people, this is a person that start a flexible activity, goes to another, and then go back. So there are some cycles and there are some motif in these networks based on this interesting behavior in the people. So it's the excitation of human mobility that generate mobility motif. And those rates, that is, if you're going to stay, you're going to move, or you are going to leave your house, these 3 rates, they're different, but in the left-hand side, we have a control experiment with 1,000 smartphones that our colleague from DTU did. And in the right-hand side, we have AirSage, that is a company from Sprint, so it's called Details Records. Notice that the value are not exact, the distributions are the same, but they are the same order of magnitude. In the left-hand side, we have only students from Denmark. In the right-hand side, we have many users, millions of smartphone users from the Massachusetts area. So this is the rate that fit our Markov models of mobility. And here it is in contrast. What I was showing at the beginning, in the lower part is the sparse data. This is the model data. And here is how it looks. You have the states, you have the completed trajectory, and you have a model to go from users to synthetic population. And this is how we now can create, with alternative methods, demand models from sparse bias data from the mobility science. And again, let me tell you the non-perfection. One thing we cannot forget is this is a person of how well can we predict? So this is very hard. Even if I do a rate, everything, I complete my trajectory. Here I have a simulated trajectory versus the data. You cannot predict exactly what you're going to do, but let me show you how you can predict this. This is one user, my own student, and their complete version. What we can predict perfectly is the distribution of number of daily visited locations in a day. This is months of data. Some days he visited 8 to 10 locations. Most of the day he visited 2. This is the stay time distribution, how long they stay in each location. What is the rank? The rank means how many fraction of time you are in your first location, second location, third, and so on. And then you have that rank of visitation is pretty good. So your home is your home, your work is your home, your gym is your gym. I don't know exactly which day you're going to go to the gym, but when you go, you stay the right amount of time. And the distance travel, if we have the data and the locations people visit, it's easy to predict the distance travel. And here is what I call the motif. The motif is this type of networks in which people move, that is not at random and is not all the combination of these sizes of network. Those are the daily mobility motif we can also predict. So we have a synthetic version of somebody that doesn't mean predicting exactly where you go. Only with 50% chance we do the exact prediction, but the synthetic population of somebody is pretty good for urban planning purposes. And here is now at the global level, I was showing you before one student. Here is all the population of the simulation of the AirSage data with the synthetic population compared with the National Household Travel Survey and the Massachusetts Travel Survey, the trip distance, of course, the OD compared to the commuting intertown, intratown, and the departure time. So here we have the demand models coming from the phones. And then let me show you fast forward to one type of application we're doing, because I told you at the beginning we want to do data science for sustainable transportation, and the challenges we have: epidemics, economic recessions, climate change, and as we know, 80 48% of the transportation emissions come from our own private vehicles in the US. Then the idea is, how can we use these data sources to try to tackle these emissions? And one aspect that drew me to this work is that the emission models we have come from very detailed data. And the purpose is, can we use data science to have a mesoscopic model of emissions that is using the mobile phone data? And here is the reason why we do this. The typical policy metric in California is vehicles miles traveled. We see through the years, and it goes. The CO2 per capita is really produced a lot by, again, what I said, our private vehicles. And what is VKT for few of us? I'm going to be call it VKT, is vehicles kilometers travel. It tells me how much somebody travel, and if he has a car, you have that amount per vehicle. So all your trips aggregated per capita, the distance per vehicle is the VKT per capita of every traveler. So we want to measure that carefully in our cities to the best of the possibilities with the mobile phone data. So we are going to gather data, in this case, from the Bay Area. We do our LBS. In this case, we're not using CDR. That is what I was showing before. Is the same method, but now with location-based service data that is come from the smartphones. We expand the data, then we have a synthetic population. And the idea is, can we predict CO2 from individual attributes of the drivers in each city? Most is, can we do a mobile data emission system? And some of the work that we have been following is that you have this population of the city with the CO2 emissions, and there has been some scaling of density of population and CO2s, but we want to go back to the original travelers. That is the objective of this piece of research. And here is what we have in our steps. So first, we have our ODs. The speed doesn't come from phones. We have the speed from Uber engines that tell us the average speed in all the streets. Then we assign the route after we have our demand model from the phones. And then we have the OD with an average speed. Then that allows us to do some detailed speed through the travel of every mobile phone users. And then we have that the fuel consumption depend on all these parameters, that is the idle time, move time, acceleration. And then we go from fuel consumption to CO2. So all this so far is standards, but we want to combine the actual CO2 model that we get, first validated, then related back to the phone data. Here are some tests we have in the left-hand side. Before the stay in place of the COVID-19, right-hand side after. So you see that we have a less emissions in the places where people commute. One aspect as we have here is the fuel economy testing our models with the standard curves of the EPA. And the big unknown in this component from the data is what cars the person is having. Then we can do our emissions depending on different models of the cars. And we're going to be using for this purpose one average car. So in a few words, like the car model, this is all individual trips, not for, basically this is a demand model of the typical commuters. We are not using truck drivers or Uber drivers. And we're going to see as a free parameter what car people is using. And here we have the validation part. We had some PEMs, so basically some sensors in the street, and then we have the PEMS NFAC at the different highways in the Bay Area. And we have our modes estimate. It have, of course, some error, but it's good order of magnitude and nicely see upper par before the stay in place order of the COVID-19, down par less. So we can capture the order of magnitude of the emissions, and we can go further with the chemistry department. We have actual sensors in the East Bay, and we also check Beacon is the name, is Berkeley something CO2 emissions, and it also have yes, that is basically led by Ronald Cohen. We have all the sensors, and we can now check in the left-hand side Beacon, in the right-hand side modes. Notice the order of magnitude, so we have big percentage of error, but the distribution is pretty well. For this is the type of error depending on the spatial aggregation. If we go 1 kilometer square is not good, but if we go 2 to 9 is good per square kilometer for the CO2, that is pretty acceptable. Then we can now have what is the VKT per person based on the different trip productions of the city. And we have different clusters. As we know, no surprise here, if we have more dense populations, we have a less VKT, and the VKT is again associated to the CO2s. And then we have the congestion also generates. So the idea is population density generate congestion, and congestion generate CO2. However, VKT also generates CO2. You have either congestion or a distance travel, and those are all the ingredients in this model. Then we have the emissions per population similar to what was already observed. Then we have, if we compare not to the population, but to the total vehicles kilometers traveled, the prediction is much better. When we go to the individual part, we have this a plot here that is the surprising part. So when we aggregate, everything looks fantastic. Then when we look into the individual trips, we see, for example, here, if we have this line is one traveler, every line is one traveler, and the different percentage of congestion. So this is the estimated CO2 of the same ODs with different congestion, which seems like daunting. So we wanted to have a interesting lesson from here, and it seems daunting. And thanks to Tuba or Stuk, the first author of this paper, she discovered something beautiful that we love to do, and that is the typical thing, what we call city science, is this plot. When you divide all the trips, again, this is every line is one traveler at different level of congestion for the same OD. when we divide by the distance travel, we have that is much more behaved. So in a few words, this is the law we discover. Y is what is your CO2 you produce. We have this constant, we have how much you travel. We have this exponential function that's how all these lines are parallel. That tells me what is the percentage of congestion. And here is in the denominator, we have the fuel economy of the vehicle. So, and this is the law here with some standard deviations. So if I tell you the car you're traveling, the distance you're traveling, and the congestion from your origin and your destination within certain standard deviations, we have the CO2 emissions. And this is what we have, the mesoscopic model of CO2 emissions from mobile phone data. And here is the gain before we have this type of uh, models that have much more details of the trips, and this is what we call the mesoscopic model. So this is a paper, it was a few years ago. VKT is the most important variable in reducing emissions. Modes allow us to extract CO2 emissions from variables easy to extract from phone data alone. And the advantage is that we not only have the travel time, we can also decide what is the route. So the advantage from having phone data is if you have Google Map, it only tells you to each of us how long we're going to travel from A to B. In the demand models, we not only have how long it's going to travel, but how many emissions they have and what is the demand that is causing these emissions. Then some other applications we were doing is if you know the demand, but the advantage is of your travelers with their phones, you can manage this demand. And we can do this game if we do lambda zero. You have that the congestion of every link depends on the travel time. Lambda zero is the user equilibrium. But if we have lambda one, we see that the cost of the trips depends on the change on the volume, and then we can do the social optimum. But of course, we cannot be the big brother that makes that everybody does the social optimum, but we can know what are the routes that bring us closer to the social optimum. And with land, in which if we have the lambda one, oops, sorry, that is the social optimum, you would have the number of trips and the benefit in the x-axis. You have that many vehicles could save 15 minutes and some vehicles needs to sacrifice. So we have the picture in the left in which you have lambda zero from this origin to the airport, you would go this way. In the lambda one, some users need to sacrifice a lot, but in the lambda 0.2, you sacrifice only a little. So in this game, we can play with this lambda and reroute for something that is closer to the social optimal. And then we can also have some aspect of looking at the network with the phone data is when you see a network and you see a number of cars per hour in a particular place, we can see who are the cars they are coming from. And we call this network road usage. And now you can have the network, the roads depending on what is the degree of the road, meaning how popular, who is using the streets, or the betweenness, how many cars are going through. So a network can have several number of cars, but it can be used locally or used globally. So this is again some way to look at different cities. And again, the take-home message of this is that when you have your route and you have your you can see every from there, and how popular it is in terms of the degree of the road. This is the network of road usage. Having that, we can see that when we check, based on this road usage, and we have only 1% reductions, but it's target by places that use the most that street, because we're going to target the most congested. What about now?
Yes, is better. Please go ahead.
Perfect. Okay, then with that targeting, we had the opportunity to go to the Rio Olympics that were in 2016, and we were able to use different data sources, including Airbnb, mobile phone data, the venue of the games, and we were able to practice this. And the idea would be, if we have all the venues and we know where the tourists are going to go and where the games are, we can target the demand. And we have also the lane where the athletes are going to go. So we would know where the places are going, which streets are going to be closed. So it's almost like the entire data-driven simulation for the games. And the idea would be, is people continue going from target or origins to target destination, if they continue using the car as usual, what would be the traffic versus if we do this target demand decrease? Then if we do with a vehicle demand decrease of 1.3%, what would be the total travel time decrease versus everybody continue as usual? And the idea is, where this target origins to destination would go, they need to increase the ridership. So we were partnered with the city in Rio, and for these target origins to destinations, they would promote the use of transit only during the Olympic Games. And I think I have a few more topics, but okay. So is
Yeah,
I see here 9:42. Should I tell you one more story or?
yes, you can go till 9:50. Our plan is to, sorry,
Perfect.
10:50 from our side, 9:50. Yeah, please go ahead.
Okay, excellent. So the latest work I wanted to show you today is urban dynamics through the lens of human mobility. And what we did in this case, it was during the COVID-19, and we were able to gather data from many cities, from after some people was graduating from my team. We ended up having collaborations all over the world. And the idea is, how can we characterize different cities from the world with this phone data? So it's like it goes back, because remember, we talked about that one of the big drivers of emissions is vehicles kilometers travel, and that depends a lot how is the shape of the city. If you have a very dense city or a sprawl city, is very different, and that is the angle we were tackling with this piece of research. These are all the cities, and here we have, let's say, from Atlanta, that is our textbook sprawl city, and we have some other cities like from Shenzhen and so on and so forth. So we have cities all over the world, and we do one simple metric that is pretty easy to extract from data, that is the radius of gyration. Given somebody, you do the center of mass, what is the center of the trajectory, and what is the distance from every location to that center. And notice in this trajectory, even if you travel a lot, in the y-axis, we have the visited location, the most visited location of somebody. Then the radius is the radius within which a person is most likely to be found. And nicely, we have RGs very different. However, they are kind of similar. They follow a log normal, with some variation, you may be thinking that the bigger the city, the larger the RG. This RG here in green, that is the largest in this sample of 21 cities, is Bogota. And the reason for that is that the majority of the population in Bogota live in the outskirts of the city, and they need to travel more. So it doesn't go as with the city size. Then we continue exploring, and one aspect I want to mention here is that here we have the RG is something from the individuals, but you can group all the mobile phone users based on the RG they have after 6 months. And then after 3 months already, your RG is stabilized. So you can keep growing if you travel a lot, but because the most visited locations in your city weigh the most, your RG is stabilized. And we already explored that it doesn't depend on the size of the city. In this picture, we are checking the different races and demographics of the city. So, for example, back to Bogota, this is a strata. Red and pink are the richest, green is the poorest. Then we have the RG notice here, pink and red, much smaller, green, much bigger. In Los Angeles, we have, let's say, poor Latino population, less travel than here, pink and red. And let's say in Boston, the suburban white, richer travels more than the poor. So in a few words, we also observed that is not a property of the economics. In Bogota, poor population travel much more. In Boston, is the other way around. So it's also not a property of the demographics of the population. And here is the take-home message. So how long you're going to travel depends how far you live from the city center. Here we're showing in Boston the different number of users according to the distance from where they live from downtown. And we have, of course, the ones that live 18 kilometers from downtown travel much more. And we have Boston is our textbook polycentric city. However, that doesn't happen in every city. In Los Angeles, it doesn't matter if you live 3 kilometers from downtown or 18 kilometers. We're having thousands of users for doing these distributions. And then this is our textbook, polycentric city. Downtown in LA, everybody move around. In Boston, they move to the downtown. Then based on this, we created a new metric that is how this distribution transform, tell us how is the shape of the city. And we measure this change in the PRG by the Kolmogorov-Smirnov test. We call it the KS for short. Then if your KS changes, you are in a monocentric city. If it's flat, you are in a polycentric city. And here now we have two ways to characterize a city. Polycentric, monocentric based on this PRG distribution, compact and dispersed based in the all way that is the population distribution. Interestingly, we have cities that are dispersed by population distribution, but also polycentric. But we also have cities that are polycentric, but they are compact, like in China. So we have cities in China that can be polycentric and monocentric, but both are compact. Then this is a new way to measure the urban dynamics. And as I said, the KS, Los Angeles is flat. We have Boston that it changes, and we have this KS number that tell us one way to characterize the city. And here we have our 2D plot and the cities go from compact to dispersed to polycentric to monocentric. And the next type, this paper was about measuring the shape of the city. However, the application would be how is it the shape of the city with the CO2 emission. That is called work in progress. At that time, we did this for the COVID-19 epidemic, and we have only data of the incidence of the epidemic for 11 Spanish cities. And see, phase one, it was epidemics, then we have the lockdown, then came the epidemics again. This is COVID-19, all in 2020. And here we have how can this metric help us explain the incidence. The few word is that RG explain the most when you have mobility. However, when in this part that there is not much infection because the people is in lockdown, our metrics help to explain better. So this urban shape predicts a little better the epidemic than just the mobility alone. And this is the conclusions of this part. Metrics that combine urban form and mobility are better predictor of spreading dynamics than population and density alone. And the future work is to include BKT and CO2 emissions into the shape of the cities. And with that, I would love to open it up for questions.
Thank you, Marta. I think we got that. So please feel free to post your question in the chat box if you have any question. Kara, you have a question. I think I saw you posted. You can go ahead and ask the questions.
Oh, sure. Hey, Marta. I think everybody wants to know where you are in a recreational vehicle, but my question in the chat box was, are people still traveling about an hour a day on average? I know there's some people who don't leave their homes. There's some people who travel 2 hours a day or more for work, for example. But has the average stayed kind of stable, even though in nations like the US, the trip rate has gone down per person?
Yes, we already have some results. For other countries, I haven't checked the change, but for the US, we start analyzing from 2019 to 2024 the changes in the COVID. And then before the pandemic, fall 2019, about on average, 5% of the population would work from home. 2024 fall, 20% works from home. So that seems to be better. However, we observed that the vehicles kilometers travel increased. That is a paradox. So it did increase, but it increased our hypothesis. We are testing this because we did that only with one data provider, and it's not enough to know if it's an artifact of the data collection. But what we are observing is that you are doing shorter trips, more trips per day. And we attribute that to the flexibility. If you have more flexibility, you are traveling a little more. And that extra in the US, and that is the sad part, is with a car.
Wow, wow. Because yeah, the National Household Travel Survey, I think, says kind of fewer trips per day per capita, but people are not really trusting of the 2021, 2022 NHTS. The 2016, 2017 NHTS is a much bigger data set. So
Yeah.
thank you.
Because several sources are showing that the BKT increase, right? They haven't seen that in the BKT has decreased, and that is what we observe. The data we use for that is Replica, and Replica is very good. They do the whole model I spent time expressing at the beginning. They do a product.
Right,
That is,
right. But it is an estimate. And yeah, the data that I've looked at, may not support it. But they should be using the same data sets that I'm looking at. So that's interesting. I'm glad you have access.
We
yes.
have Thank you, Martha and Kara. So we have another question from Ipsita. Did you get a chance to compare two cities of similar urban form and obtain different travel patterns?
Oh, that's a great question. I didn't look at it. Yes, that would be the typical situation when you do the scatter plot, then you have something and then you have the variance. I am very worried about the global trend, but
Mhm,
that is the typical thing we would like to express. And the idea is, of course, some cities are using more cars, and the whole story, what I'm observing is that we did this same plot for the US.
mhm,
And what we are observing is that the US are much of them dispersed and polycentric, with some exception, but we are more in this, definitely in the dispersed part of the story compared with Chinese cities. And then the idea is that we are so dispersed that that is one of the headaches. Our design of the transit system is harder. It's not, there are many reasons, but the fact that we need to serve a population that is all sprawl is harder for the transit system. Then the idea with the shorter trips with the car, we need to start thinking in how to bring the facilities where the people, bringing the people to the facilities or the facilities to the people to avoid the dependence on the car. Well, it's a big
mhm.
topic. We are just measuring and the solutions we need to build together, I think.
Yeah, I think we have a question from John that our question is, please comment on the impact and importance of the rate of growth in personal vehicle electrification. If you have
Mm.
any comments on that. Kara put some information, reply to John's comment. So anything, you have any comment?
Eh, in California, so basically, as we know, electric cars are not going to decrease the traffic nor the car dependency. And we have a lot of, I have a lot of colleagues in city planning that are not very keen on investing uh, in electric cars because the car dependency of the US. I cannot forget this, the fuel efficiency in the VKT. So if we have, or the motivation slide that I have, if we have less fuel cars, we are not decreasing car dependency, but we are having less CO2 emissions. So it has to be, I mean, in the US, we're having shared, electric, and autonomous. No, those are the
Yeah,
topics we are investigating now.
yeah. So I think the future you will have some results maybe on that. I have one question on you started with this mobile data. Yeah. I'm a very privacy person. Like I don't share any location or anything. But at the same time, I have very, soft corners towards data. I wants to get data and I also wants to provide data. My question to you is that as a researcher, how do you think that we can collect good quality mobile phone data without compromising the privacy to convince person like me that, yeah, you can actually share data, it's in good hand? What's your comment on how you're thinking in future on that?
Yes, that's a big topic, so big that I have a colleague from MIT, Sandy Penland, who went to the World Economic Forum to discuss this data about privacy. My point is very personal, that we need to treat this data as a human subject research. So if it's handled properly, it can really help. And in fact, it was clear that this data became more available post COVID-19, where everybody wanted to have the movement of people to see how the epidemic was spreading. Uh, I think if it's treated like human subjects, the privacy and is the individual well-being is meant to be protected, and it cannot be affected in the name of research. But I know I'm not very fan of now some companies are monetizing the data, and in the name of privacy, they are giving us aggregated data or worse data or even products as opposed to the raw data. There is a lot to learn. And I'm not, even if I created the models myself, I don't want them to be black box. I want that the research community have access to the algorithms, that we create the models, that we
Mhm.
create the knowledge for social good. Then I understand the data is delicate, but well, I work on it, and I think we, as a researcher, because I always say some in some of my presentation is governments have access to the data when they need it for investigations. Companies have access to the data. Then, if we would be advocating for privacy, we ourselves, researchers, are losing the access to the data. And I am an advocate that researchers need to have access to the data.
That's fair point. No, thank you, Martha. I really appreciate. We are at 11 now. So I also thank everyone for joining this session. As you can see, we posted on the chat box that there are 4 parallel sessions starting now. And one session is public transit and operation, which will be in this call. You can stay here. And the other 3 sessions will be going on parallelly. You can join any of them. I really appreciate Martha. Please thank Martha, and you can put your emotions in through the online thing. And thank you all for joining. Those who can stay, you can stay, and otherwise you can join other sessions.